Okay, folks, we're going to go ahead and get started here. All right, everybody can see everything? We're good? We're settled in? Excellent. Okay, so last time we left off, we were talking about flipping chairs. Oh, come on. It was a pun. Okay. Remember that when we flip the chair, we're not going to switch a substituent from one side of the plane to the other. The cis-trans relationship between any pair of substituents on the cyclohexane ring is going to be independent of your chair conformations your species is in. So if they were on the same side before, they're still going to be on the same side. Just like when you flip an actual chair, the legs stay on the same side, right? Yeah. And one leg doesn't suddenly come to the other side just because you flipped the chair. That'd be called breaking the chair. Okay. And so these substituents that are cis to each other are going to be on the same side still. The zones that were trans to each other are still going to be trans, right? That's not going to be interrelated to flipping the chair. The cis-trans relationship of any pair of substituents is going to be unaffected by your chair flip, and typically you want to go ahead and represent those with Hawthorne projections. This being the Hawthorne projection. All right. So did everybody see those Hawthorne projections okay? Right down here. Fantastic. Now, what have we done? We have essentially written these out as if they're planes, right? Can you see it okay? So we write them out as if they're a flat chair or table or plane, right? And then we represent the things that are on the top or bottom of that. Now remember, it doesn't matter the configuration, the conformer you put this in. The things on top stay on top, right? The things on bottom stay on bottom. Okay? And so the Hawthorne projection can tell you, for example, these two things are cis to each other, right? These two are trans to each other. Yeah. And that's not going to change. It doesn't matter which boat conformation or chair conformation or any of that. Okay? Okay, so when we represent these in Hawthorne projections and start doing chair flipping, every substituent on the cyclohexane ring is going to favor an equatorial position rather than the axial position. How much it favors that typically is a factor of how large that is. Okay? Larger substituents are going to be more energetically favorable towards being equatorial. Right? Axial positions are very high energy, the larger you are. The most stable chair conformation can usually be predicted for a number of disubstituted cyclohexanes by looking at this right here. So here we have a Hawthorne projection, right? And these are cis to each other. This is a 1,3 substitution. Everybody okay with that so far? Okay, fantastic. Now, the 1,3 substitution, are these things going to want to be squeezed near each other or put further apart? Further apart, right? And so the diequatorial position is going to be the more stable one, right? The diaxial position is going to be considerably higher energy. Okay. This right here is the trans. See they're on the different side? Okay. So this 1,3 position, if we have one of these in the equatorial position, what does the other one end up being in? Axial, yeah. And that's because those alternating positions, right? Whenever we did equatorial and axial. Now, that means that there's not one that's more favorable than the other, is there? At least not when they're the same thing. Because no matter what you do, one's an equatorial, one's an axial, isn't it? Okay. And so these end up being equally favorable. It doesn't really matter in this case. They're degenerate. They have the same energies. So this is model kit. Did anybody buy a model kit? No. Not at all? Okay. Okay. Would anybody like me to post a model kit that's reasonably priced? Could somebody send me an email reminding me? Because I'm not going to get to do it until like 4 p.m. after I deal with another class and 3 more meetings. Okay? Okay. And I will put up a link to a reasonably priced, reasonable model kit. Okay. Okay. So anyways, if you do this with a model kit, this is the chair conformation, and you can actually see when you put these up on there, it becomes quite obvious how they're pointing out, right? Can you see that three-dimensional figure? Actually helps you quite a bit, doesn't it? Can you see this jutting up over the ring here and taking up a lot of space? Yeah, it's quite nice. And that's the other way, and you end up with one equatorial, one axial. And these end up being energetically equivalent. Okay? Okay, so let's talk a bit about constitutional isomers. Let's first start with identifying the constitutional isomers. Another way of calling constitutional isomers is structural isomers. Okay, they're just two names for the exact same thing. They're going to share the same molecular formula. They will differ in their connectivity. Note if you use IUPAC naming, you're going to actually see the difference between these two things, right? Okay. So for example, these right here, these are constitutional isomers. They're not connected to anything like each other, are they? No. They're quite obvious when you actually look at the molecule or you look at the IUPAC name, right? But if you were to write these just number of carbons, number of hydrogens, they'd be the exact same, wouldn't they? Okay. And so those are constitutional isomers. These right here, these are not constitutional isomers. Okay? Why would that be? They're actually the exact same molecules, aren't they? You see, I've literally just taken this and moved it down this way. Can everybody see it okay? Yeah. So, literally, they're like flipped of each other, aren't they? And they have single bonds between everything that would be freely rotatable. Okay? Okay, so that's the two things you gotta watch out for constitutional or structural isomers, is that they have to have the same formula. That's exactly correct. They have different connectivity, giving you different structures, but they have to be permanently differently connected. They can't just be conformations of each other, right? If you can rotate and flip it back in place, it's not a constitutional isomer. Okay? Okay, because they don't actually have different connectivity. You've just rotated them to look slightly different. Okay? This is probably, if you're going to make a mistake, and it's not just, I don't know what a constitutional isomer is at all, this is probably the big mistake that you're going to make. Okay? It's the most common mistake other than just not knowing anything about it all. Okay? So the rules for identifying constitutional isomers. For each molecule, identify the parent chain or ring. This is, again, the longest continuous chain or ring of carbons that contains any CC double or triple bonds. You will note that this is very, very, very similar to what? IUPAC naming, isn't it? In fact, this is why you do IUPAC naming the way you do. Okay? You're literally dividing up constitutional isomers so you can give them names that would identify which one's which, right? Yeah. So number 2 is going to be the number of carbons in that chain or ring. So again, make sure the carbon atoms involved in the double or triple bonds receive lowest numbers, or there are no such multiple bonds. First substituent is attached to the lowest number of carbon. Establish the relative connectivities along the parent chain or ring. This would have been the positional identifiers, right? Before with our substituents, where we would have went through and figured out this one's on second carbon, this one's on third carbon, right? Then in this case, we don't actually have to write out the name if we're just identifying either the constitutional isomers, okay? But again, those are the locators. Now, the size of the parent chain or ring, the numbers assigned to the carbons involved in multiple bonds, the numbers assigned to the carbons in which any substituent is attached, the identities of the substituents attached to the same number of carbon. Otherwise, the molecules have the same connectivity. They are not constitutional isomers if they have the same connectivity. They would be one of the other ones, or they're the exact same molecule. Okay? They could be conformers as well. Note, by the way, that if you want, you can just wholesale write out the name for this. Like, if you just sit there and write out IUPAC names for everything, you'll end up getting this. Because you'd end up with the same IUPAC name if you do all the rules right. Okay? Okay. If they're the same IUPAC name, can they be constitutional isomers? No. No. Because they have the same connectivity, don't they? Okay, so again, these ones right here, so we look through this. Again, we do the numbering off to give the lowest numbers here, right? And then we do the longest parent chain, and that's that 6-carbon chain, isn't it? Okay? And it threw everybody off because I put the carbon chain going straight here, and the carbon chain is curved in this one, isn't it? And so your brains went, obviously different. Yeah. Different shape. Saturated molecules containing only single bonds and no rings. So when we do these constitutional isomers, one of the things that will help you out is the index of hydrogen deficiency. Another way of saying this is the degree of unsaturation. The degree of unsaturation is probably the more popular way of saying that because it's the older terminology. Okay? So the saturated molecules containing only single bonds and no rings, this is going to set the degree of possible saturation you have, or the possible degree of hydrogens you have, right? The max number of hydrogens. Molecules that contain double, triple, or rings, double, triple bonds or rings, are going to be said to be unsaturated. And this is because they'll have fewer hydrogen atoms than you could possibly have on them, right? Anybody ever heard of a saturated versus unsaturated fat? Or trans fat? Yeah. Same rules. That's actually talking about this degree of unsaturation. Okay? That's what that always was. So your index of hydrogen, IHD, is going to be a fairly common abbreviation. Please sort of get used to that so you're comfortable. Of a given molecule is going to be half the number of hydrogen atoms missing from the molecular formula of an analogous, i.e. same number of type of each non-hydrogen atom, saturated molecule. I.e. if it wasn't in rings, if it wasn't in a double, triple bond, and didn't have those features, how many hydrogen atoms could you have? Okay? Okay. Now, each double bond is going to contribute 1 to the molecule's hydrogen deficiency, right? And again, that's because each carbon involved in a double bond has lost how many hydrogens? 1, right? Okay. Can everybody understand that a double bond would take up 1 hydrogen off of each carbon involved in it? Okay. Okay. Each triple bond is going to end up having a 2 contributed to the IHD. Okay, and again, is everybody comfortable with that? A triple bond takes up 2 hydrogens off each carbon?
That's 2 each, right? So
Yeah.
Yeah. 4 in total? Or would you just
No, for the triple bond it's 2. So if you had 2 triple bonds, it would be 4. But a single triple bond is only going to take up 2 IHD. Does that make sense? Okay, and so each ring is going to contribute 1 to the molecule's IHD, and again, that's because you lose that end cap hydrogen on both sides, right? Okay, and the IHD, even though it says hydrogen deficiency on this, I think the new terminology is actually more confusing. The old terminology, degree of unsaturation, was very direct in its meaning, right? That it's literally the number of features that causes you to be unsaturated. Okay? And so a double bond has that extra pi bond, right? 1 on saturation. 2 pi bonds, 2 on saturations. Ring, 1 on saturation. Okay? Anyways, I got to teach you IHD because the committee decided that. And I did not get an opinion on that one. Just like the new versus the old IUPAC for the damn double bonds and naming in the first place. If anybody wants to join that committee, you can express my dissatisfaction. Okay? Okay. So why should constitutional isomers have the same IHD? Why would that be? Okay. So if we have the same number of carbons and we have the same number of hydrogens, they could be constitutional isomers, right? So they'd have the same formula. But every degree of hydrogen deficiency actually removes 2 hydrogens, doesn't it? So if you remove hydrogens from the formula, are they the same formula? No. No, they can't be the same formula, can they? And so automatically, if you have degrees of unsaturation, you can't have constitutional isomers if you have different numbers, right? Because by definition, they have different formulas then. Okay? Okay, and this actually shows you an example of this. This is the fully saturated form right there, which is ethane, right? Then we have 1 degree of unsaturation, which is ethene. Notice the number of hydrogens. What happened? And we lost 2, didn't we? Yeah. So automatically can't be constitutional isomers, right? They have different numbers of hydrogens in the formulas. Okay, this is 2 IHD, and so that is lost 4 hydrogens, didn't we? Okay, anybody have any questions about that? Notice it doesn't need to be carbons to have IHD. For example, we have oxirane here. That's a cyclic one that has an oxygen in it, right? But the same rules overall apply. See that again, we've lost. We have 1 IHD. We end up losing 2 of the hydrogens. See that? Okay. Mm-hmm.
So they're not isomers? Or...
No. These are not constitutional isomers.
Okay.
Yeah. They can't be constitutional isomers. And so this is one of the ways to very quickly confirm I can't have these as constitutional isomers. If they have differences where like one doesn't have any double bonds, one has a double bond, bam, done. Not constitutional isomers, right? Okay, what is the IHD of naphthalene? Okay, everybody ready? We're gonna do this. So please use your QR code to join me on this. You can work the problem on your tablet or whatever. We won't be using those anymore. Yeah, I'm replacing those with this because people were losing them every class. Like a stream of 4 or 5 people in some of my classes. And then people would pick other people's ones up and start using those instead. And so it turned into a bit of a disaster. So this one hopefully will be a little bit less of a disaster. Okay. Okay. And so what is the IHD of naphthalene? It's working. Does everybody see that you can actually like upvote options and stuff? Yeah. Okay. Okay, so what elements does this have that would cause it to have IHD? Yeah, 2 rings, and we'd have 5 double bonds, right? Yeah. Okay. Okay. Has everybody done their answer? Fantastic. Okay, and you guys are exactly right. Perfect. That was excellent. Does anybody have any questions about that? No? Okay. Yeah, it's actually like one of those things that really the problems you might have are making it more complicated than it is, right? Because you think it has to be harder. So let's talk about calculating these based on molecular formula rather than looking at a full structure and having to deal with all that. Okay? There's actually a very, very easy way to do this. Every carbon atom in a chain has 2 carbon atoms connected to it, right? So if we are a straight chain, then every single carbon atom has to have how many hydrogens attached? 2, right? And these are called methylenes. They're the middle parts of the chain, aren't they? Okay. We also have to have 2 ends to a chain, don't we? And that means the number of hydrogens on a straight chain is always 2 times the number of carbons plus 2. Okay? And so that's the formula for the saturated hydrocarbon of whatever type, right? Okay. Is that clear and everybody's okay with that so far? The 2 n is the lengths, then plus 2 n's, right? Fantastic. If you ever forget the formula, by the way, you can just logically deduce it. Just write a couple saturated hydrocarbons, and then count them up and see how it divides by the carbons, right? So every chemical formula for a saturated hydrocarbon has to look like that, doesn't it? Have you guys ever done this for sugars, by the way, in biology? No? Okay. Okay. That's okay. We can make adjustments for other atoms like nitrogen, oxygen, halogens, right? If we have a halogen, how many hydrogens are going to go on the halogen? None. Halogens only make 1 bond, right? So by definition, bond has to be consumed, doesn't it? Yeah. How about an oxygen? If we have an oxygen, how many bonds does an oxygen usually make? 2, right? And so that has to actually drop the number of hydrogens from what a carbon would be, wasn't it? So those 2 extra bonds that would have went to hydrogens if you had a carbon, they don't exist, do they? So every oxygen would be a -2, wouldn't it? Okay. How about a nitrogen? How many bonds does a nitrogen usually make? 3. And so, yeah, nitrogen is going to have 1 less than a carbon, wouldn't it? Okay? Okay. So right here, this is the saturated hydrocarbon. Everybody's good with that so far, right? Fantastic. Okay, this one's the one with the oxygen. So the oxygen, it's not going to have any effect on your hydrogen atoms. You just don't count it. We can avoid the entire issue of an oxygen by just not counting it in our numbers. Okay? Okay. And so we count up the number of carbons. That number of carbons times 2 plus 2, right? Your oxygen literally just slots in between one of the hydrogens or one of the carbon bonds. And we can just wholesale ignore it. Okay. If we have a nitrogen, well, the nitrogen is 1 less than the carbon, or another way of looking at that is if we slot it in between a carbon and hydrogen, we have to add 1 hydrogen, right? Okay. So your number of carbons plus 3, right? Okay. And so this actually just straight up adds like that plus 2 does. Is everybody okay with that so far? Okay. Okay. Now, halogens, those actually take the place of a hydrogen, don't they? Because the halogens have the same bonding pattern as the hydrogen, doesn't it? In fact, you can kind of think of the hydrogen. Oh, my periodic table's up like that again. God, I need to mount that somewhere. You kind of can think of the halogens or the hydrogen as being sort of an honorary halogen, right? It's a halogen that doesn't hold on to its electrons well. Okay. Okay, so let's determine the IHD for a compound whose molecular formula is so. I'm kind of trying some different stuff in this, by the way, this first one. I think I kind of have a plan for how I'm going to incorporate these better. But let's try this out and see how this one works, okay? So does everybody have the formula so far? Okay. So make sure you get that formula. And then we're going to go on to the Slido. And what I'm going to do is I'll have audience Q&A on here so that you guys can answer free form in text. Okay? And I just want to see how that works out. I think it probably won't work out as well as I'd like. But I'm a scientist, right? What do scientists do? Try it. Yeah. Yeah. We gotta actually prove ourselves wrong, don't we? Okay. Okay, everybody got your formula? Fantastic. Okay. Okay. So your IHD for the compound with that molecular formula, and you should be able to QR code and then have throw up answers if you'd like. And yeah, it does show the previous Q&As, so don't worry about that. It should, as you guys answer, pop in there. In the future, I'll probably be using the Q&As before the problems, and then we'll go on to a quiz like I've been doing for the other ones as the problem itself. Okay? But I want to try it out. Okay. Is everybody able to answer the Q&A? Get into the Q&A?
So we type it in on the Q&A section like we're asking questions.
Yeah, like you're asking a question. Yeah, just throw up an IHD number that you think it is. Yeah. Okay. Yep, and I see people are working through it. So the first thing you have to figure out is the saturated numbers of the hydrogens, right? And then you need to figure out how far off of you are you. Okay? And then the number of hydrogens that you are away from being saturated, what do you have to do to that number? Yeah, you gotta divide that by 2, right? Because IHDs are each 2 hydrogens. Okay. So I think I proved that to myself that this is not the way to do it, right? Yeah. This is a lot more friction than the other way, isn't it? Well, no, the previous problem that we did, where you guys selected an answer. Okay. Okay. So we're going to move on now. So again, we count up our number of carbons, right? So that's 7 carbons. The saturated one would have what? 2 times 7. And then we would add 2 to that normally from the carbons, right? So our saturated one would be 2 times 7 plus 2 for just the carbons, right? Now we need to look at the nitrogens and oxygens and chlorine, okay? What do we do for nitrogens? Add 1, so it's plus 1 now, right? What do we do for oxygens? A grand old nothing. Ooh, got a little break. Okay. And what do we do for the chlorines? Subtract 1, exactly. And so we end up plus 1 nitrogen minus 3 chlorines, right? So 16 plus 1 minus 3, that's 14, isn't it? Okay, and I saw some people throw that up while they were working through things, which actually was kind of neat to be able to see that. But then let's see, we have 14 hydrogens. How many hydrogens do we actually have in this molecule? Yeah, we have 8 right there, right? So we take that difference. That difference is 6. So we take 6, that's the number of hydrogens we're short, aren't we? Okay. To get the IHD number, you always have to take that number and divide it by 2. Yeah. And so that gives us a final IHD number of 3. Okay. Did I lose anybody here? Okay. All right, so this is the again, drawing all the constitutional isomers for a given formula. This can be more challenging than you'd imagine. You can actually start getting to ridiculous numbers of constitutional isomers once you start getting long enough. But this is how you can systematically do that. Okay? Anybody know why you might need to do this? What if you do a reaction and you don't actually know exactly what product you're going to make? But you know how many carbons got in the end product. So what you do is you figure out all the constitutional isomers that you have. Then you'd use another method to eliminate some of those. You'd use another method to eliminate more. And eventually you eliminate everything but what it is. Okay? And that's how you figure out, like, you synthesize a totally new drug, never been seen before. Like, which was the one that people used to take a lot in, like, the early 2000s, 90s, and it makes you feel less depressed? Not Zantac. Starts with a Z. Xanax. Thank you. Yeah, you got it. Yeah. That drug actually was mispatented. Did you guys know that? Yeah. They had actually patented a drug that was not it. They patented a molecule that was not the drug they were producing and selling. And so somebody came along and was like, oh, we made this drug and it does the exact same thing. That's an $8 billion a year industry. We should sell this as a generic. And the company, of course, sued them and said, hey, our spectra are exactly the same. Everything's the same. And what they found out is they had the wrong damn stereochemistry for it. They had the wrong isomer that they had patented. They had no patent on their $8 billion a year cash cow. Do you know the scientist that was the lead of the scientific council for that?
No.
My advisor. Yeah. My advisor was the one that actually showed that I had the wrong patent for the wrong drug. Yeah. They'd screwed up monumentally, right? Yeah. So let's draw all possible backbones. What we're going to do is, again, we're going to get the formulus IHD. This is going to tell you the possible combinations of your double bonds, triple bonds, and rings that you would require for those isomers. You'll then draw all the possible backbones, leaving out the double bonds, triple bonds, or halogen atoms, because you can add those later and they don't affect the overall structure. Okay. You'll then include rings. The number of rings must not exceed the IHD computed from step 1. You can do different sized rings. Each structure, however, may contain fewer rings than the IHD. You can't have more rings than the IHD would allow, right? For each structure generated in step 2, you would then add a double or triple bonds to achieve your total IHD that you calculated in step 1. Yes, this means that if you have like 5 carbons, then you're adding 4 different structures, all with double bonds in different places, right? And so, yes, it can get extremely long. For each structure generated in step 3, add halogen atoms at various locations to generate as many unique connectivities as possible. No, I won't make you do this for a large compound in an exam. It would take all class period, okay? but I might make you do 1 or 2 of them, right? Okay. Okay, so let's determine the IHD first. Okay. So what would be the IHD for this? Yeah, yeah. We don't have any double, triple rings, none of that, right? Okay. Okay, so what's the next step? We're going to then draw all isomers of it that have no double bonds, triple bonds, or halogens. We're not going to do the halogens yet. That means don't do the fluorines at this step. Okay? So we have to put 4 carbon atoms. We have no double bonds, triple bonds. We don't put any halogens yet. We don't put any rings. We can't do any of those. Okay? And so we have a straight chain here, right? And then we also have the branched one, don't we? Okay. Okay. Is there any other ones that we could do that would be unique? No. Yeah, if we try to move this methyl anyway, we just end up with the straight chain again, don't we? Yeah. Okay, and so again, we have no double or triple bonds because we have an IHD of 0, right? So the next part we're going to go on to is the halogen. So we're going to add fluorines in. So we add a fluorine into this straight chain. We can put it on the first position or the second position, right? Okay. And those will both be different. Why can't I put it on the third position? Same as the second, right? It just left, right. Okay. And again, fourth position, same thing, right? That'd be the same as the first position. So. Okay, this one here, we can add it in 2 different places. There's 2 unique places to add. We could put it on one of the branches, or we can put it in the center, can't we? Okay. So the next part, we're going to add the second fluorine. Now note that this is actually going to cause you to branch further, right? We're going to get more constitutional isomers, okay? So we start with the ones that have fluorines on the first positions, right? And then we add it, both fluorines first position. Okay, that's unique because that's the first one we've done, isn't it? Okay, now the second fluorine is going to go on the second position. That's also unique. It's not the same as the first one, is it? No. We add it to the third position. Then we look at our previous ones. It's again unique, isn't it? Okay. And then we add it to the fourth position, and again, that one is not the same as the previous ones, is it? And so we made 4 constitutional isomers by adding that second fluorine. Okay? Okay. Now, what if we start adding them on to the one where it's on the second position? Remember that first one we did? We put our first fluorine on a second position here, right? So now we start adding that second fluorine onto those ones. So we add it to the first position, and what do you notice about that one? Yeah, those are the same, aren't they? Yeah, that's not unique. So that's not a constitutional isomer. Okay? We then add it onto that second position again, and that one is unique, isn't it? We add it onto the third position, and you will note that, again, that one's unique again, isn't it? Okay. We add it onto the fourth position, and it's not unique again, is it? Because we can flip this around, and it would be similar to that I right here. Okay, is everybody seeing how you go through and do this? If you need to generate all of them, yes, it is a fairly long process. You're going to finish by adding the second fluorine atom to the various locations, eliminating any duplicates. This is the remaining ones where we did that branch structure. Does anybody need me to go through that, or are you getting the idea? Okay. Okay, so this is drawing all the constitutional isomers of something that has an IHD of 1. Okay? I just want to make sure that we have an example of this so you understand what's going on when you look at one of these. So, again, this molecule here ends up with an IHD of 1. If we go through and do the saturated versus unsaturated, right? Like we did in the previous problem before. So our structure has to contain either a ring or a double bond in it. Can it have a triple bond? No. Triple bonds have an IHD of 2, don't they? So we can't have a triple bond. But we can have a ring or a double bond. Okay? So these are some examples of constitutional isomers that would have rings in them, right? And see how we can just move our oxygen through into the ring, then expand the ring out. Okay? And then this right here is going to be ones that contain no rings, but we could add a double bond in, can't we? Okay? So we have to write them out for now so we can add the double bond in later to the various different positions it could go. Okay. So the structures without a ring, we're going to have to add our double bonds. We have to add this without introducing formal charges. What does that mean? Can we add a double bond to something like this right here? No, oxygen doesn't want 3 bonds, does it? Yeah, that would add formal charges. There's no halogens formula. We don't need to do that step. However, do keep in mind that, for example, L and K here, those are redundant, right? So whenever you do these structures, you should always need to go back afterwards and double check that you didn't make redundant structures. Okay? That is the hard part. Generating these rules help you quite a bit. And so if you just follow the rules and are very careful, you'll generate plenty. However, figuring out which ones are redundant can be quite tricky. Okay? You gotta be very careful, very methodical. So this is leucine and isoleucine. What do you think the iso typically stands for? Isomers. Iso typically stands for their isomers of the other one. So these are going to be 2 naturally occurring amino acids. They're constitutional isomers. They have the same molecular formula, but they differ by the connectivity. Can everybody see it okay? This is connected right there. If you moved it over here, it'd be that one, wouldn't it? Okay. And so the monosaccharides provide many more examples of constitutional isomers. Almost every constitutional isomer that could exist does for the monosaccharides in some way, shape, or form. It's quite extensive. So these are the constitutional isomers of sugars, acyclic and cyclic forms of these sugars, acyclic being the straight chain, right? Cyclic being the rings. Have the same formula, but they're going to have different connectivities. They are constitutional isomers. Do you know which one the sugars typically exist in? Which form? The cyclic. Most sugars exist about 90-something percent, usually 99% or so, in the cyclic form. Okay? In your body, these have a reaction where the ring opens and closes pretty consistently. Okay? And so that ring open close reaction happens quite often. We will actually cover that reaction a little bit later in the semester, in case you're wondering. So these are the monosaccharide isomers. Ribose and ribulose are isomers. They differ by the location of a carbonyl group. And you can actually see that right here. Everybody say okay? And you just move the carbonyl group, constitutional isomers, right? In the ribose, the carbonyl group is going to belong to what's referred to as an aldehyde. Everybody remembers aldehyde now from our naming? Yeah, kind of. Okay. Ribulose, the carbonyl is going to be a ketone. That's the ketone right there. By the way, has anybody ever heard of aldose and ketose? No? So in biochem, you might hear about them. And aldose, aldehyde, right? Ketose, ketone. Okay. In the ribulose, again, the ribose is classified as an aldose. Ribulose is classified as a ketose. Glucose is similarly classified as an aldose. Fructose is actually the ketose structural isomer of that. Okay. All right, so these are the saturated, non-saturated in fats and oils, which is probably where you've mostly heard this terminology before, right? And so this is actually a saturated fatty acid. This is butyric acid. It's found in rancid butter. It's that smell and taste if you ever have rancid butter. This right here is stearic acid. It's a pretty major constituent of beef fat. This is oleic acid right here. This is a major constituent of olive oil. By the way, is burning something really harshly with olive oil particularly healthy for you?
No.
No, it actually reacts that bond. Yeah, you'll actually react away that bond if you burn the olive oil. Yeah. And it's fairly easy to do. So you gotta kind of heat at a moderate temperature if you're gonna work with olive oil. Also, it is fairly easy to vaporize the olive oil. So, and yeah. Linoleic acid. These are the essential fatty acids, by the way. Anybody know why they're essential? We need them to live, but why do we need them to live? Like, we need we need like cholesterol to live. We need glucose to live. Why aren't those essential? It's the things we produce. So we don't produce these structures, and they're essential in our diet because we have difficulty, if we can at all, produce them. Okay? So most essential, like essential fatty acids, we just don't produce at all. But we need those structures to make other stuff. Okay? Anyways, safflower oil, flaxseed oil, you get the idea. Anybody have any questions about this? Okay. Does a typical American lack essential fatty acids in their diet? Kind of a trick question. Yeah, most Americans don't lack most of the essential fatty acids, but there are a few of them that people sometimes don't get. For example, the one in fresh corn is actually fairly rare for people to get. Yeah. So the effect of double bonds on the fatty acid melting points, you may have noticed that when we're unsaturated, we have much lower melting points, don't we? When we're saturated, what do we notice about the melting point for a similarly sized fatty acid? A lot higher, right? So if we were working for these things, like when we're actually working with them, if I took this oil right here, and I'm in my kitchen, I'm trying to use it, what sort of form is this oil going to be? Or this fatty acid, as it were. Is it going to be liquid or solid? That's solid, isn't it? When I throw it in the pan, it'll liquefy. But it's going to be a solid that I'll scrape out and throw in there, right? By the way, this is actually what they used to use at McDonald's. And then there were protests. McDonald's replaced it with, I believe it was peanut oil. And then after that, there was protests against peanut oil because it was supposed to be unhealthy for you, and they replaced it with seed oil. And funny enough, every single one of those replacements is less healthy for you. So, I don't know what to tell you there. You gotta wonder sometimes, right? Okay. So anyways, what do we notice as we have greater degree of unsaturation? Yeah, lower melting points. So if you wanted to make something like peanut oil so you could spread it on as a solid and it melts while it's on, like, say, hot toast, what would you do to it? Decrease the degrees of unsaturation, right? Or you would saturate it. Yeah. And that's how you make peanut butter. You saturate a portion of the peanut oil. Okay? I know. Okay, so this right here is the double bond. Notice it makes that kink in the structure. Without the double bond, these would freely rotate to the most energetically efficient ones, the lowest energy ones, right? Which would give you basically a straight chain, right? Yeah. Okay. And so again, this is because this is a what type of arrangement for the double bond here? Cis. Yeah, that's a cis arrangement. And that's where the trans fatty acids versus cis fatty acids comes. That's what that always was. Okay? Okay, anybody have any questions? Okay. Does anybody ever heard of like a omega fatty acid? That's the position of the double bond. Okay? Literally as done in an a Greek alphabet. Alpha, beta, gamma, omega. Yeah. Everybody has heard of like like 2 trans, 3 trans? No? 2 cis, 3 cis? Or 2 on substitute, 3 on substitute? No? Okay. Many of the fatty acids that are essential to our diet are actually di and tri on substitute. And it's because we don't have the ability to make this stuff in our bodies. We just don't have the enzymes. You can talk to Dr. Phillips about why we don't have those. Okay. Anybody have any questions at all? No? Okay, we will move on to the next one. How's the app going? Okay? Okay overall? The QA answer to the question wasn't so great, right? Yeah. The